Okay, welcome back, everybody. Give me 1 second here. All right, just a couple of things before we continue. Everything that's been turned in, I have graded that requires my grading. I've noticed a couple of things, especially the activity number 3 that dealt with the conversion. If you completed that assignment, which, by the way, short reminder, assignments like homework and activities, they remain open. Yes, they have a due date, but they remain open until the end of the semester. So if you miss an assignment, you can still go back and do it. Okay. 1 second. Except that as per the syllabus, there is a late fee involved with that. Okay, so but you're going back and doing it. Some points is, as I stated before, is some points is better than no points. All right, so yeah, go back and do them if you want to. Totally up to you. It's your education here. So what I was trying to say is, on the last activity where you did the conversion, by and large, everybody did very well. Set that up for a while. And those who did complete it, I did attach the key for that assignment so you can look at your answers. The biggest problem I saw really is not a problem. It's a matter of giving your answer with the correct number of sig figs. Okay. Because I've seen answers that gave all kinds of digits, and which suggested that your answer is more accurate than it really was. And that's the whole point about sig figs, is presenting your data no more accurate than the data that you use to create the number you did. Okay, whatever you did to it mathematically. And so, as a quick reminder, when the question says leave your answer with the correct number of sig figs, the first thing that you should think of is, number one, what am I doing mathematically? Okay, because that's going to determine how you're going to present your data with the correct number of sig figs. If, number one, you ask yourself, am I multiplying or dividing? If that is what you're doing to the problem, then significant figures. Your answer, if you're multiplying or dividing, should have no more sig figs than that number that has the least number of sig figs. Okay, straightforward, I hope. All right. The other part of the question you ask yourself is, am I adding or subtracting? Okay, if I'm adding and subtracting to the problem, then you need to think in decimal places. Your answer should contain no more decimal places than that number that has the least number of decimal places, because that number with the least number of decimal places is the least accurate. Just like when you multiply and divide, that number with the least number of sig figs is the least accurate. Okay, and don't mix the two up. If you're add and subtract, sig figs don't have anything to do with anything. Decimal places do. If you multiply and divide, then yes, sig figs have to do with your answer. Second point, remember the difference between a measurement and an exact number. Exact numbers are like, for example, 100 centimeters in a meter. That's an exact number, okay? Or a dozen equals 12. That's an exact number. Therefore, exact numbers don't play a role in determining how many sig figs you have if you use that factor in your calculation. Okay, those are exact numbers. All right, enough of that. Are there any questions? Don't forget, today you have your first exam. It is 75 minutes long. That's the time allotted. It is timed. You have until 10 p.m. It is open now, so give yourself plenty of time. Please don't wait until 9:30 to go in there, because at 10 p.m. Canvas will shut it off. Okay. All right. Any Any questions concerning chapters 1, 2, 3? If not, I will jump into chapter 4 and get into chemistry. Chapter 4 is fairly short. I almost got it completed today for my 1 o'clock. It was about 3 slides short, but you'll see the first couple of weeks is kind of intensive with a lot of stuff given to you. Things should kind of spread out a little bit more now with the chapters coming up. Okay. All right, then. Well, no questions. Then we proceed with chapter 4. In this particular chapter, we're going to, go back to chemistry. We're going to talk about how the atom is put together and what our model is for the atom. Okay. Let's start with what is called Dalton's atomic theory. And note the date here, 1800s. 1800s, scientists started trying to figure out what are atoms all about, how they put together. And bear in mind that, the scientific equipment we had at that time, not the best, but nevertheless still gave us a foundation for the model that we have today. It changes as we get more data. Everything I tell you today, it might change tomorrow, for all I know, when new data shows up. Even the short time I've been in chemistry, the theory has changed somewhat. All right, so Dalton put across this atomic theory. He suggested that an element is made up of tiny, indestructible particles that are called atoms. He called them atoms, which that term itself is not a new term. Atom, the term atoms go all the way back to the Greek times. But it turns out that they're not quite indestructible, because we know that the atoms are actually made up of what are called subatomic particles. Now, we're going to work specifically only on protons, neutrons, and electrons. Those are the subatomic particles that we're going to deal with. Those guys are really made up of smaller particles themselves, which is beyond the scope of the class, but it was very, very fascinating science there. Okay, so not quite indestructible particles. We also propose that all atoms of an element are identical, which is true, and have the same properties, which is not true. Okay, and we know now that having the same atom, depending on how they're put together structurally, can change the properties completely. Classic example is a diamond. Diamond made up of carbon and graphite, or it's a dry lubricant, which also has carbon, very slimy, it's a dry lubricant. Okay, totally different properties, yet the same element involved. Okay, so not quite the same. This part is quite correct in that atoms of different elements combine to form compounds, and that is the definition of a compound. Okay, so what we have here is, I'm sure you hopefully recognize, we have a model of 2 diatomic elements, which could be anything. I'm just going to label those G to G4 green, okay? And then it's going to react with 2 red elements, also diatomic, okay? And then they're going to react to form 2 separate compounds with 2 different elements, okay? So we have 2 compounds. And so I'm just going to call that 2RG. R and G just represent some atoms and combine. Now you can see here a couple of things that we need to take away from this. Is that one, there is what is called the conservation of matter. This is one of the laws of physics, laws of chemistry, that matter is conserved. We not create matter, nor do we destroy it. We just move things around. And so you can see that we have 2 red two reds here that are diatomic in a certain form. And yet, at the end, after the reaction, we still have two reds. They just happen to be in a different form. It is still two atoms of the red. Same is true for the green. I got two greens here, two atoms or whatever they may be. And then we still at the end have two at the end as products. So this is what we call a balanced chemical reaction, okay? And then we got this coefficient right in front that tells us the ratio of reactants is a 1-to-2 relationship. That relationship, we're going to utilize it down the road quite a bit, but we're also going to learn how to balance chemical reactions, because from balancing chemical reactions, it gives us these coefficients. Okay. All right, let me make sure the sound is being shared. Now, another aspect about the theory is that when compounds come together, the elements, I should say, when they come together in whole numbers, in whole ratios, not quarter, not three-quarters, not impartial. And so, for example, when hydrogen and oxygen come together to form a molecule of water, there are two hydrogens for every oxygen. When the oxygen happens to be the central atom, which I designate as follows, and then the oxygen, I should say, then the hydrogens are bonded to the central atom, represented by this line here that represents a bond between the oxygen and the hydrogen. Okay, so they come together in whole ratios, whole numbers. Atoms of two or more different elements can come together in different ratios to form different compounds. And so if we look at the example here, where you get carbon and oxygen come together, you can generate what we call carbon monoxide or carbon dioxide. Here, the red could be carbon and the gray could be oxygen. Here's carbon and then bonded is the central atom, and two oxygens bonded to the central atom of carbon. So here we have carbon monoxide. Notice the naming, mono meaning one, there's one oxide, one oxygen, compared to carbon dioxide, meaning there are two oxygens, okay? Note the prefix is di and mono, okay? So totally different compound. Carbon monoxide, deadly gas. Carbon dioxide, good for plants, okay? Could be deadly for us too if it displaces all the oxygen. So deadly in that sense. Now, so we start 1800s and then, that decade toward the beginning of 1900, I should say, the new millennium begins, and it starting at the 1900s, we're going to find there's a lot of work being done, a lot of work. So British scientist, name of good old J.J. Thompson. He is given credit for the discovery of the electron way back in 1897. He also should be given credit for the precursor for the old-fashioned television that we used to have. I know some of us may still have them. Got rid of mine not too long ago. It's a big old heavy-duty, definitely on a flat-screen television. Those are heavy guys, so and I'll explain how that worked here in a bit. So what he did, he determined that he used this what we call a cathode ray tube that created a particle, okay? And this particle was shot along this pathway, and it hit a surface that was coated with a chemical. Now, with any particle with high energy, when it hits something, it transfers that energy onto the other particle. And it excites the other particle it hit. It transferred the energy to. Now, nature being nature, nature doesn't like to stay up in what is called an excited state. It drops back down to the ground state, okay? Because it got excited, but it has to go back down. And conservation of energy, just like we did with conservation of matter, has to follow. And so what happens is the energy it gained gets released as light. Now, with that information, JJ set up this following experiment. I got it set up for sharing the sound. So if you don't hear it, tell me if you don't hear the sound. And I think all of you should be able to hear
it. A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate.
Okay. And so these particles are being generated from the tube, and these particles come across and hit the screen up front. As I was stating, as it hits the screen up front, the energy that particle has is transferred to the material on the surface, and that particle on the surface gets excited, and then it goes back down to the ground state, and in doing so, emits light. So you're over here on the right side, watching television, so to speak. This is the precursor. You're watching TV and the thing's lit up. Obviously, a television has a lot more to that, but the same principle occurs. Even in LED screens, as you're looking at the screen you're looking at right now, these particles in the surface are being excited. And when they're being excited, they go back down to the ground state and have to emit energy. And what the emit energy is light. And that's what you're seeing when you look at that screen. There's these particles being excited and going back to the ground state and getting kicked back and forth, back and forth. It happens so fast that you think it's nothing's happening there, but it is. All right, let's continue.
Called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by...
And noted here, there is a plate, electrical plate that is passed. Now, charged particles have along with it a charge on it, but they have a magnetic component. Okay, so everything that you got electricity running through a motor, there's a magnetic component. That's why we're able to make either an electric motor or we make a generator. We're playing either with electricity or playing either with a magnet. Anyway, the fact that there is
by the plate bearing positive charges,
electrical plate here, it deflects that current. That suggests that beam must be charged. Okay, specifically, look at this. It is being pulled toward the positive plate, which suggests that beam must have a negative charge.
Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a...
And like I explained earlier, any moving charged particle has within a magnetic component. And so if you place a magnet here, you're going to cause that beam to be deflected. Here, the south deflects the beam, or you rotate that magnet, you can have the magnetic track. So back to the old-fashioned televisions, the reason they were so heavy in the back, they had two giant magnets that were controlled by the television signal. And it made the scanning of the screen, and obviously there's more to it, but to actually see an image on the screen. But it was all due to particles, charged particles. Electrons.
Tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thompson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thompson determined the charge-to-mass ratio of an electron to be negative 1.76.
Okay, obviously we're not going to have you be responsible for this equation. The takeaway here is he was able to calculate this ratio of E over M. That number on the right side of the equation and the equal sign is a constant. Okay. Now, once he knew that ratio, and E is the charge to mass ratio, if he knows the charge, he can rearrange that equation, and guess what? He calculates the mass. So obviously you can't weigh the mass of this particle. It's so tiny. But with this equation, he was able to get a mass calculation of the electron. Extremely tiny.
Times 10 to the 8th coulombs per gram.
Okay. So
a cathode ray tube.
What he proposed, now here is early 1900s, now is we're deep in, not deep, we're into the 1900s. So what he proposed based on his data and other experiments, that he proposed that the model of an element of the atom was that of what he called the plum pudding model, where there is a positive component in the atom someplace, and then there's a negative component someplace in the atom. Okay, hence it was all scattered out, sort of looking like plum pudding. So that was his model, but it didn't last very long with respect to the model, because along comes another scientist, note the time, 1911 versus 1904. Okay, now what he did was take some of the similar experimentation using similar type of equipment, but in his case, he was able to generate what are called alpha particles. The important thing here is they're big, giant particles, okay? And he took these particles and he bombarded a gold foil. And then around the gold foil was the detector, very similar to the one JJ had, okay? Now, he was proposing, thinking that if we had the plum pudding model was true, then these particles would just shoot right through the gold, and that'll be it. Well, to his surprise, the particles that were being shot through the gold were actually, in some cases, being ricocheted, okay, at an angle, and sometimes is even shot back to the source itself. And that was quite astonishing, because that suggested that in the gold foil, at least in the gold atoms, there must be a very heavy duty chunk of matter. And with that, he proposed that must be a nucleus, or the proton that has a center. So let's listen to his experiment.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles.
I'm trying to stop it with
some
this.
Even back in the direction.
Look carefully, you can see on the, here is a point. This is the particle coming through. Here's the gold foil, and here's where most of the particles are hitting on the surface. But then occasionally you see areas where on the side starts to angle off, and so they were angling off from where he didn't expect them to be happening.
Direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So it's sort of like shooting pool, you know, that cue ball hitting that ball and you're trying to get in the corner, so angling out. So what he proposed was a new model, Rutherford's nuclear model, which is shown here on the right. And the left is Thompson's plum pudding model, and which didn't last very long. So the new model was based on Rutherford's work, where in the center there is a nucleus. And we learned later on that that nucleus is basically where the proton exists and another subatomic particle, which is the neutron. At this point, the electron, we don't really know specifically where it's at, other than to say that it's got a negative charge, the proton's got a positive charge, and the electrons are kind of like our solar system, kind of three-dimensionally though, wrapping or orbiting around the atom. Okay, so 1917, Rutherford, he's credited with discovering the proton. J.J. Thompson is credited to, when I say proton slash nucleus, okay? And it was not until 1932 that another British scientist, Chadwick, he is credited for actually discovering the neutron, okay? And so we had J.J. with the electron, Rutherford with the proton nucleus, and then Chadwick with the neutron. And our model now is sort of like what you see there on the right, where in the center you have the nucleus where the proton and the neutron exists, and then the electron is orbiting and by some manner around it. It did find out that we did determine that atoms are basically a lot of empty space. For example, to give you kind of relative description, is if I were the hydrogen atom and I was my scale, I represent the nucleus, which in that case for the hydrogen only has a proton, but then my electron, which would be orbiting around me, would be roughly about 3/4 of a mile away. Yeah, that's a lot of empty space in between. Okay. Another analogy would be if the nucleus was the size of a small marble, and then the atom itself, the size of the atom would be about the size of a Cardinal Stadium. All right, so we have these subatomic particles, okay, specifically the electron. Okay, its symbol is generally a letter lowercase c with a superscript hyphen representing a negative, because it has a negative charge. Its location is outside the nucleus. We don't know at this time where, but we're going to learn that here, where specifically it exists. The proton is in the nucleus, and its symbol is P superscript plus, and it's inside the nucleus, okay? And then the neutron has the letter N, and it also is inside the nucleus. Now, we give a charge of a -1 to the electron and a +1 toward the proton, whereas neutron has no charge. The thing to take away here is for the elements, they have an equal amount of electrons and an equal amount of protons for a net charge of 0. Okay, and we're going to learn how many protons they have and how many electrons here in the next few slides. Now, because these chunks of matter, so to speak, are very, very, very tiny and small, what was created is a relative mass, an atomic mass unit, which is the relative mass. They assign the proton and the neutron essentially a AMU of 1, a unit of 1. Okay, the electron, being so small, essentially was given a mass of 0. Okay, it really isn't 0, but it's so tiny it's essentially a zero mass, but yet it has such a large effect on the chemical properties of all around us, because all chemical reactions occur because the electrons, that's where all the action is, on the electrons. All right, so atomic notation. How do we write the atomic notation? Well, first of all, we have, let me pull up the periodic table first. This is the periodic table that we ask you guys to use. And if we look at, sorry. If we look at, let me zoom in a little bit. Let's just take carbon. Zoom in quite a bit. Okay, and so we have carbon right here. We have a number on top of the symbol. The symbol for carbon is C. Okay, the number below the symbol is the atomic weight. Okay, the 6 is the atomic number, which is a whole number. Okay, every atom has their own, every element has their own unique atomic number. Notice that next to carbon is nitrogen, it has 7. Okay, now that number represents the number of protons and the number of electrons. And so you can, using a periodic table, be able to determine for any of the 118 elements how many protons it has. So if you look at carbon, carbon has 6 protons and 6 electrons. There's 6 positives and 6 negatives to give you a net 0. Let's take a look at fluorine. Fluorine has 9 protons and 9 electrons. Selenium 34 has 34 protons and 34 electrons. Bromine has 35 protons and 35 electrons. Okay, and each one has an atomic weight underneath, which is a decimal number. Okay, now I'll make a note here. We don't use those atomic weights, if any, are calculations to determine sig figs. And we'll talk about why that's the case. And I can tell you quickly. It's because those numbers, the decimal numbers, are the average of whole numbers. And that means that those numbers have an infinite number of sig figs, so we don't use them to determine whether the number of sig figs in our answer. Okay, treat them as exact numbers, and then that way you remember. Okay, so the way to use the atomic notation is we have SY, which represents the symbol, and then we have what's called a mass number. Okay, a mass number is a whole number, just like the atomic number is a whole number. We're going to learn how to calculate, determine what the mass number is, and the atomic number is specifically the number on the periodic table. Okay, the mass number we need to calculate sometimes. Okay. Now, the atomic number, as I stated, is the number of protons and the number of electrons. So element number 100 has 100 protons and 100 electrons. Element number 1 has 1 proton and 1 electron. The big takeaway here is the protons. The protons define what that element is. Okay? The moment you gain a proton, you have made a totally different element. And so carbon, for example, which has 6 protons, is still carbon, whether it's in the form of, let's say, a hydrocarbon big long chain hydrocarbon that you burn, or in the form of a fatty acid in our body. It is still carbon with 6. It just in different forms, okay, but it's still carbon. All right. Now, for elements, we're going to eventually talk about these elements that are on the periodic table that are going to lose or gain electrons. And that forms what are called ions. You may be familiar with the term electrolyte. So when you're drinking a juice and you're thinking, okay, I need my electrolytes. Well, you're not ingesting the element. You are ingesting the ion of the element, which means that that element will be either lost or gain or electrons, okay? Lost or gain electrons. Right. So the mass number, how do we determine the mass number? Okay, well, the mass number is the sum of the protons and the sum of the neutrons. Now, every element, the number of neutrons within the element can be different. When that happens, is we create what are called isotopes. And so you may have heard like carbon 14 dating, carbon 13, carbon 12. Okay, those are all carbon. With the way what they differ is by the number of neutrons. Okay? But how do we determine the mass number? Well, first of all, we use the periodic table. Now, the most common isotope for any particular atom is determined by looking at the atomic weight, okay? Look at the atomic weight, and then rounding it up to the nearest whole number. All right, so here we have carbon, okay, which has an atomic weight of 12.01. If we round that up to the nearest whole number, that number becomes 12. Look at 14, excuse me, nitrogen. For nitrogen, that number is 14. For oxygen, 16. For phosphorus, it's 31. Okay, now what that tells you is that when I do that for carbon, I can write carbon hyphen 12 is the most abundant isotope for all the carbon isotopes. And I did that by rounding the atomic weight up to the nearest whole number. Nearest whole number, okay? Now you will get things like carbon 11, carbon 13, carbon 14, and those are only different from the most abundant carbon they differ by the number of neutrons. We'll get some examples here in a little bit. Now, here's the thing. Now, let's take the number 5. Well, let's go. Okay, 11, 12, 13, and 14. Take those 4 numbers, okay? Can anybody tell me the average of those 4 numbers? 11, 12, 13, and 14. What is the average of those 4 numbers? Come on, 11, 12, 13, and 14. You don't even need a calculator. You look at those numbers and tell me what the average is. But if you want to do a calculate.
It says the chat is disabled.
The chat is disabled? Oh, really? What's going on here? Okay, try it now. Somehow, what is the average of 11, 12, 13, and 14. 12 and a half, exactly. Okay, 12 and a half. Now, like your exam, or all your exam, your homework and assignments and so forth for the class and in a lot of classes, there is a weighted number for it, right? And so if, for example, there was like, I don't know, number 12 existed 90% of 98% of the time, and 11 was, I don't know, call it 1%, and then maybe 0.5% for 13 and 0.5% for 13. Now, as I take that average, every number, 11, I have to multiply by 1%, 12, I need to multiply it by 98%, 13 by 0.5%, etc. So I get what's called a weighted average. A weighted average now no longer is 12.5, but guess what? It is 12.01. Okay, just like the atomic weight for carbon. And that is because carbon 12, which is the most common isotope, there's about 98% of it in the environment, so it has more contribution. And therefore, that is why we can take any element here and round that number up, the atomic weight, to the nearest whole number, and that tells us what is the most common isotope for that element, okay? Because it is the weighted average. Okay, so, and the way they differ between carbon 11, carbon 12, 13, and 14 is simply still carbon there. All of them got 6 protons, but all of them got 6 electrons. Where they differ is the number of neutrons. So carbon 12 has 6 protons, 6 electrons, and 6 neutrons. Whereas carbon 13 has 1 more neutron, 7. Carbon 14 has 2 extra neutrons relative to 12. Okay, and that's why those numbers are decimal numbers, and that is why we don't use them to determine sig figs, because they have an infinite. They come from whole numbers, and they're the weighted average of whole numbers and have an infinite number of sig figs. Okay, let's go back to that. So the mass number is the number of protons plus the number of neutrons, which are whole numbers. Now, the mass number, what we do to determine that is this. Carbon atoms, for example, always has 6 protons in the state. Okay, and since carbon is number 6 and has 12.01, the most common isotope is carbon 11, right? And so carbon 12, excuse me, would have 12 protons. 12, oh, what am I doing here? Wake up for it. 6 protons, 6 electrons, and 6 neutrons. Okay. Let me do some examples here. We talked about that. So how do we calculate the neutrons? So we rearrange that equation. The mass number is the number of protons plus the number of neutrons. Rearrange it, we get neutrons is equal to the mass number plus the number, minus the number of protons. Okay. And so going back to carbon as an example, which was as follows. Okay. The mass number is 12. You take the atomic weight and round it up to the nearest number. Okay. The number of protons is simply its number 6 there. Okay. So guess what? The number of neutrons is 12 minus 6. So we have 6 neutrons for carbon 12. Okay. If we dealt with carbon 11, then that becomes 11 minus 6, which now is 5. So carbon 11 would have 5 neutrons, but it'll still have 6 protons and 6 electrons. Okay. Carbon 13 would have 6 neutrons. And this is where we talk about rounding up to the wholest number. Keep it in mind when we do that using the atomic weight, that is the most common isotope. Okay, because occasionally, what they will do is give you this kind of problem and say potassium 40. Okay, you might think, well, is that the most common isotope for potassium? So let's do this periodic table. Let's find potassium. Who can tell me the most common isotope for potassium? Potassium is K. I circled it. And just by looking at it, which is the most common isotope, the most common type of potassium there is? What do we got? Exactly. Potassium 39. Can we just simply take that 39.1, round it up to the nearest whole number, which is 39. Okay. Now, with that in mind, look what they're asking you here. They're talking about potassium 40. So obviously, that is not the most common isotope that there is. Okay, so they're asking you to work with that. So we're going to find the symbol for potassium. Hold on 1 second, please. Okay, and that's K. Okay, this is the atomic notation. 40 is given to you in the problem. Okay. And 19, well, we're going to find that from that's the atomic number. We find that from the periodic table. Now, we needed to do potassium 39, we do the same thing. There'd be 39 and 19. They both have the same, it's still potassium. They have the same number of protons and the same number of electrons. Where they differ is the mass number. So obviously potassium 40 must have 1 more neutron than potassium 39. Okay. In fact, it has 21 neutrons. So how many neutrons would potassium 39 have? What? Well, I'll answer that in a second. How many neutrons would potassium 39 have? Not 39, 20. Exactly. See, this one here is for potassium 40. Okay. Potassium 39 has 20 neutrons. Okay, these two are isotopes. Potassium 40, potassium 39 are isotopes. All the elements technically are isotopes. The most common isotope that's there is simply determined by taking the atomic weight and rounding it up to the next whole number. And that gives you the most common isotope because, again, like I explained earlier, that is the weighted average of the mass numbers of all the isotopes. That's why I asked you to figure out the the atomic and the average for 11, 12, 13, and 14. And we all agree that the average of that is 12.5, no question in it. But the weighted average is different. And if carbon 12, number 12 was 98%, then all of this would be, the weighted average would be closer to 12, so about 12.09, okay? And that is the weighted average of all the carbons. Now, you asked the question, why there's 21? Well, simply because it has an extra neutron. Potassium 40 has an extra neutron relative to potassium 39. Okay, the most common potassium form is potassium 39. That has 20 neutrons, 19 protons, 19 electrons. Okay. I don't have a percent composition for potassium 40, but it's okay because we know that potassium 40 has the same number of protons and the same number of electrons as potassium 39. They only differ between the two by 1 neutron. That's why potassium 40 is 40. It's got an extra neutron. Does that answer your question? Okay. And we'll do some more examples here in real clear. So here we got this one. Okay. It says write the atomic notation for bromine 81. Well, I would first of all ask myself the question, hey, is bromine 81 the most common isotope? And I got to know the atomic number anyway, so I go look up bromine. So I need the periodic table, okay? And bromine's right here. Bromine, what is the most common isotope of bromine? Which bromine would be the most common isotope based on the periodic table? We bromine 80, exactly. You got it. Bromine 80 because it is, take the 79.90 and round it up to the nearest whole number, and bromine 80 would be the most common isotope. And we need 35 for the atomic number. Okay. So obviously bromine 81 is not the most common isotope. So the difference between bromine 80 and 81 is 1 extra neutron. Okay. So they had the same symbol. Okay. Same atomic number. Where they differ is the mass number. So for the most common isotope, it will be bromine 80 and 35. Okay. And now we subtract those two numbers to tell us how many neutrons. So bromine 81, you're just going to label it BR81, has 35 protons, 35 electrons, and 46 neutrons. Okay. Bromine 80 has 35 protons, it's still bromine. Okay. 35 electrons, but how many neutrons would it have? Anybody know? How many neutrons would bromine 80 have? What's 80 minus 35? Well, if bromine 81 had 46, exactly, it'd be 45 over here. Okay, because the difference between these two is simply 1 neutron. They're both of them, that's the important part. They're both of them bromine. They both of them have 35 protons. They both have 35 electrons. Where they differ is the bromine 81 has an extra neutron, it has more weight. Okay, a little bit heavier because of the excess weight. It's like hydrogen. Hydrogen, there's 3 types of hydrogen. there's the hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 1 has no neutron. Okay, hydrogen 2 has 2 neutrons. Hydrogen 3 has 2 neutrons, 1 and 2 neutrons, respectively. Sorry, got carried away. 0 for hydrogen, the most common hydrogen. 1 for hydrogen, what we call hydrogen 2, and then hydrogen 3. Okay, or that hydrogen is used in what we call heavy water, and deuterium and tritium. Anyway, they only differ with each other because the other extra neutron, which does have an effect on their properties too. All right, so isotopes. Isotopes, basically what I've been talking about. Isotopes of an element have the same atomic number, which means the same number of protons, the same number of electrons, but their mass number changes depending on how many neutrons they have. In this example, we got carbon 12, carbon 13, and carbon 14. Carbon 11 also exists, okay? All of them have 6 protons and 6 electrons, but they differ respectively in the number of neutrons. Carbon 12 has 6 neutrons. Okay, carbon 13 has 7 neutrons. Carbon 14 has 8 neutrons. Okay, everybody there has 6 protons and 6 electrons, but vary with respect to the neutrons. So here we have a table to kind of demonstrate everything. And we've got 3 isotopes of oxygen. Now, who can tell me, looking at your periodic table, of these 3 oxygens, which one is the most common isotope? You got oxygen 16, oxygen 17, oxygen 18. Which one would be the most common isotope, and therefore the most abundant isotope out there? Exactly, and that would be oxygen 16. Okay, and all you'd have to do is just look at the periodic table, round up the atomic weight, which is already at 16. Now, all of them are going to have the same number of protons, right? Because protons define what that element is. So all of them are oxygen. So they all have 8 protons and all have 8 electrons. I'm talking about the elements, okay? Where they differ is the mass number, which is given to you. You don't have to calculate that. Oxygen 16 means a mass number of 16. Oxygen 17, here's the mass number 17 and 18 respectively. The number of neutrons is simply 16 minus 8, 17 minus 8, 18 minus 8 to give us 8, 9, and 10 neutrons. Okay. Obviously, as I stated, this is the most abundant, most common, I should say, or most abundant isotope in nature. Okay. And there are the other isotopes around. In fact, they're all around us. We ingest these isotopes, and not like they're just hanging out there all by themselves. They're just all around us, unless you synthesize them and you make specifically. There's a whole area of chemistry, organic synthesis, where you actually will make certain compounds with a specific isotope in their structure, because some of them are radioactive, and then as the patient injects them, they're able to follow and see what happens, to see where the material goes when it gets metabolized. All right, so the atomic masses in the periodic table are what are called the weighted average of all the atoms. Okay, and that's why we can do that. Here's and do what I mean. What I meant was that's why we can take that whole number or the atomic weight and round it up to the whole number, and that gives us which is the most common isotope. Okay. So, here for a second. And so here's again, this examples of carbon 11, 12, 13, and 14. Carbon 12, roughly about 98.89%, carbon 13, roughly about 1%, and there's trace amount of 11 and 14. Okay. And so you can see there's a lot more abundant carbon 12 than 11, 13, and 14. And so when you take the average of those four numbers, 11, 12, and 13, and 14, and take into account the percentage contribution overall, and that's why you get a weighted average of 12.0 for carbon, okay? And so you get 12.01 for the weighted average atomic weight for carbon. And that's why we can bring this up to a whole number, round it up to a whole number, and that gives us the most abundant isotope for that element. All right. Okay, now you may be asked questions here, and you know what, we'll probably be done with this chapter here. That's good. All right, so you got a problem here. You're asking, okay, using the periodic table, determine which is the most abundant isotope. Is it lithium-6 or lithium-7? All right, well, no problem. You look at the periodic table, and we look for lithium, and lithium is over here, number 3, and its atomic weight is 6.94. All right, so you take that 6.94, round it up to 7. So lithium-7 is the most abundant isotope of these two. Okay. Next question is, okay, well, what about chlorine-35 or chlorine-37? You do the same thing, pull up the periodic table. Okay, look for chlorine. Chlorine is right here. You can see taking that 35.45, round that up to the nearest whole number, that becomes chlorine-35. Okay. Chlorine-35 is our most abundant isotope, and so that's the answer. Now, again, you didn't have to memorize anything, just looking at the periodic table. Now, we refer a lot to the periodic table because with the information you have on hand now, you should be able to look at any of the 118 elements and determine a multiple of things. Here, I'll start. Okay, let's take sulfur right here. Okay, well, what do I know about sulfur by just looking at it, finding it on the periodic table? One, it's number 16. Therefore, it has 16 protons. It has 16 electrons. Okay. Its most abundant isotope is sulfur. I'm going to just put S for sulfur, 32. Okay, well, how many neutrons do I have? Who can tell me that? How many neutrons does sulfur 32 have? About 16. Okay, 32 minus 16, isn't that 16? So it has 16 neutrons. Okay. All right. What else do I know about sulfur? Where is its position? Is sulfur a gas, solid, or liquid? That's correct, Tom. Is sulfur a gas, solid, or liquid at 35 degrees? 30, yeah. It's at 32 room temperature, 32 degrees. 25 degrees Celsius, I was thinking Fahrenheit. Is sulfur a solid, liquid, or gas? Gas, we got one gas. Okay, you might want to look at that, that table that I had that showed which ones were gases, which ones were liquids. There's only two liquids, so it's not a liquid. Gas, you got two gases. Are you guys sure? It's a solid at room temperature. That is correct. Okay, so what do we know now? It's a solid at room temperature. Yep. And that's why I emphasize the temperature. All right, so what else do we know? Is it a metal, non-metal, or a metalloid? Okay, that's good. It is a non-metal. Okay. Now, I also stated being a non-metal, does it have a tendency to gain or lose electrons? You remember what I said about that? Gain electrons, that is correct. Okay, so gain electrons. Now, here's the $1 million point question. Can anybody tell me, yes, it's going to gain, but how many electrons is it going to gain? There's a specific number that it's going to gain. In fact, everybody, I'll give you a hint. Everybody in this group are going to gain, the nonmetals are going to gain the same number of electrons. Okay, that's hint number one. It's going to gain, and that is correct, 2 electrons. It will gain 2 electrons, okay? And by gaining 2 electrons, what is its new overall charge? As an element, it has a 0 charge because it has 16 positives, 16 negatives. But if it gains 2 electrons, what is its new overall charge? It will be negative by -2 because it gained 2 electrons. That is correct. So I would write it as S -2. Now, finally, and that is the ion that will be it would create. Now, finally, of the 16 electrons, that sulfur has, and given that these electrons are in layers, energy layers, can anybody tell me how many of those 16 electrons are on the outermost layer? In fact, everybody in that same group would have the same number of electrons in the outermost layer. How many electrons would that be? Look at the group it's in. 6, you got it. Okay, it has 6. So of the 16 electrons, there are 6 valence, I'm going to call it VE, valence electrons. Okay, valence. So look at all that information you just learned just by knowing its position on the periodic table. And we can go through the same exercise for any of them. We can go next door to chlorine, and do the same thing. 17 protons, 17 electrons. The most common isotope for chlorine is chlorine 35. Okay. And from that, determine how many neutrons it has. We would learn that it's a gas. Okay. And at room temperature, and it tends to gain electrons, specifically 1, and it have a -1 charge. In fact, once it becomes a negative charge, you change the name. So sulfur, like we were doing, becomes sulfide. Chlorine becomes chloride. Okay. So all of it based on its position in our periodic table. We can do all this only for those elements that are the A elements of Roman numeral A. These guys in here, we can't do that too much because they vary in the number of electrons that you can lose and gain. Okay. So that's using the periodic table. All right. Let me finish this up, and I think all right. So some elements are radioactive and very unstable. It just means that they just fall apart and emitting a lot of radiation, a lot of energy, and all these different particles. So anyway, these elements that you see and with the parentheses, these are the ones that are radioactive, and because of that, they decompose very rapidly and actually can't hang around long enough to study them and learn more of their properties. So anyway, element number 6, curium, named after Madame Curie. Side note, anybody by chance know where Madame Curie is from originally? I can tell she won 2 Nobel Prizes. Throwing trivia stuff. Well, Madame Curie originally was from Poland. Okay, she went to France because France was during the time period the Mecca of science at the time, and she went there to study science with her future husband, Curie. Anyway, the reason she did that because in Poland at the time, women were not allowed to get a college education or move up in their education. So she went to France to get an education and get her degree, her doctorate. Anyway, chemical formulas, they tell us about the types and the number of atoms present in the molecule. They don't really tell us anything about the order itself. They just tell us, and we're going to learn more about the order and how things are bonded and put together. But for example, H2O just tells, at this point, tells you there are 2 atoms and 1 oxygen atom to give us a total of 3 atoms. Okay. And we're going to learn about bonding later on. We're always going to tell you who is the central atom, and then everybody else around it is bonded bonded to the central atom. In general, the very first atom is normally the central atom, with the exception of H2O. By convention, it's written as H2O. Okay. For example, if we have the general formula of C3H3O3, okay, don't need to know about what it is at this point, but be able to recognize that there are 3 carbons, 6 hydrogens, and a total of 3 oxygens in that molecule. So there's a grand total of 12 atoms. Okay, that is a general formula, something that if you like to eat Italian dressing, you probably ingest a lot of that. It's a general formula for acetic acid, but that's not important. The takeaway is be able to determine that there are 12 atoms in there. Okay, now you see this next one here. I believe it's the last example. We'll call it a day. Is you see a parentheses. What that tells you is that within that parentheses, there is this unit. We're going to do a lot about that. We're going to deal with these units, which are called polyatomic ions. And in fact, there are 2 of these units around the parentheses. So what that means is that there are there are 2 nitrogens and a total of 8 hydrogens, okay? And 1 carbon and 3 oxygens for a grand total of 14 atoms total in this particular compound, which by the way is called ammonium carbonate. Ammonium carbonate. So here we're just trying to tell you that, show you that these be able to count how many atoms of each. Eventually, we're going to be able to take the atomic weights of each one, okay, and add it along up. We get that from the periodic table. Add up the contribution of every atom in its atomic weight, and that gives us a overall what we call a formula weight for that compound. And then we're going to be able to take that information and be able to determine the percent composition of how much percentage of carbon in that compound, how much of hydrogen, how much oxygen. But right now, identify the different types of atoms and how many total. Okay, so for example, we got H3PO4, 3 hydrogens, 1 phosphorus, 4 oxygens. Okay. Ca parentheses OH and parentheses 2, 1 calcium, 2 oxygens, 2 hydrogens, a total of 5 atoms. And then Al and in parentheses SO4 and parentheses subscript 3, telling us there are 2 aluminums, 3 sulfurs, 12 oxygens, and a grand total of 17 atoms in that particular structure. Which, by the way, the first one, if you like soda pop, like I do, it's phosphoric acid, a lot of acid. Calcium hydroxide is the second one, and aluminum sulfate is the third one. I'm not worried about the names right now. We'll eventually get to that. All right. You know what? I thought I was going to end it here, but yeah, last one. Sorry. Law of definite composition, meaning that yes, when water gets together, there's 2 hydrogens and 1 oxygen, which corresponds to 11.2% hydrogen and 88.8% oxygen. And we're going to learn how to calculate that. Okay, we're going to do those later, but that is the composition of water, regardless if it's water obtained here or on the other side of the world. Water is water. 11%, 7.2% hydrogen, 88.8% oxygen. Okay, sorry about that. Went over just a tad, 3 minutes, but congratulations, we're done with chapter 3. Okay, chapter 4, excuse me. All right, and if we stop share.